So this is ELC111, Introduction to Electricity, and this presentation is on the decibel. Before we talk about the decibel, we need to talk about logarithms. Logarithms were developed centuries ago as a means to simplify mathematical operations. So take an exponential expression as the one shown, y equals b raised to the x power. And this expression can be restated or re-expressed as x equals the log of y to the base b. So that's how this expression is read, x equals the logarithm of y to the base b. Now, simply expressing an exponential as a logarithm doesn't really benefit us. The benefit mathematically from the logarithms is due to the properties of logs. And the first property we'll look at is that if we take the log of x times y, this equals the log of x plus the log of y. And if we have the log of x divided by y, this equals the log of x minus the log of y. Another property of logarithms is that if we have the log of x raised to an exponent, then that exponent can be brought around in front as a coefficient. So I can take the exponent n and move it around in front of the expression as a coefficient, as we see here, n times the log of x to the base b. And the last property of logarithms that we'll look at is the log of b to the base b equals 1. Now, we find in mathematics that we commonly raise 10 to some power, and this is how we move the decimal place to the left and the right. So 10 is commonly used as the base of a logarithm. And because it's commonly used, there's a special symbol for log base 10, and that is log. Now on your calculator, you may see this as lowercase log or capital Log. It depends upon the calculator. So the logarithm of y to the base 10 is expressed as the log of y. So the 10 is just inferred. Now, a number we commonly raise to a power in science and engineering is e. Now, e equals 2.718281828. It continues on. And e is sort of like pi. Pi is just a number. Pi, as you know, gives us a numeric relationship between the area of the circle and the diameter of the circle. And of course, also pi gives us a relationship between the circumference of a circle and the radius of the circle. And E simply describes the rate at which things increase and decrease in nature. So it's quite common to find an exponential expression such as y equals e to the x power. So e is also commonly used as the base of logarithms, and because it's commonly used, there's a special symbol, and that special symbol is ln, and you'll see on your calculator a key that says ln. So the logarithm of y to the base e is written as ln y, which is simply the log, the natural log of y. Now, when we look at electronic um, circuits and or systems, we quite often discuss these with respect to their gain. Gain is symbolized with the capital letter A. And gain is simply the ratio of the output, either power, voltage, or current, with respect to the input, again, power, voltage, or current. So the power gain of a circuit is P out over P in. The voltage gain of a circuit is V out over V in. And the current gain of the circuit is I out over I in. Now, if a circuit or a system has a gain greater than 1, then it is considered to be an amplifier. If the gain is less than 1, then the circuit is said to be an attenuator. So these are two terms you may encounter when discussing electronic circuits and systems: amplifier and attenuator. Now the decibel. The decibel, typically recorded simply as lowercase d, capital B, D for the metric prefix deci. It was originally used to express reductions in audio levels in telephone circuits, and it was based upon the loss of in an audio telephone signal over 1 mile of cable. And they decided to name this term, this quantity, in honor of Alexander Graham Bell. So the decibel expresses or provides a logarithmic relationship of P out with respect to P in. So equation 1 shows you that the decibel equals 10 times the log, and this is log base 10, the log of P out over P in. And of course, the multiplication factor of 10 here is why this is called a decibel. Now, the decibel can also express the logarithmic relationship of V in and V out. So equation 2 shows us that the decibel equals 20 times the log of V out over V in. Now let's look at a few calculations. We're given that the input power to an amplifier or a system is 500 milliwatts. The output power is 10 watts. What is the gain in decibels? Well, we start with equation 1. The power gain in decibels equals 10 times the log of P out over P in. We substitute in our known values. 10 watts is the output power, 500 milliwatts is the input power, and this has a gain in decibels of approximately 13 dB. Now the precise value, or this value, is actually closer to 13.01 dB, so hopefully you can appreciate why I have used an approximately equal symbol here. This is not a precise value. Now let's look at another example. We're given that the input power is 50 watts and the output power is 10 watts. What is the gain in decibels? Again, we start with equation 1. The power gain in decibels is 10 times the log of P out over P in. We substitute in our known values. The output power is 10 watts and the input power is 50 watts, and we end up with approximately equal to negative 7 dB. So notice, if you will, in the first example that this circuit or system was an amplifier. The output is larger than the input. The second is an attenuator. The output is smaller than the input. The amplifier has a positive gain in decibels. The attenuator has a negative gain in decibels. Now, we can also use or calculate power levels with respect to the input and output when we're given the gain of the amplifier or system in decibels. So we take equation 1, and from our definition of the logarithm, we can rearrange or re-express this as P out over P in equals 10 raised to the dB divided by 10 power. So let's look at an application of this. We're given that the input power is 1 watt, the gain is 23 dB. What is the output power? Again, we start with the equation we're given, P out over P in equals 10 raised to the dB divided by 10 power. We substitute, or we rearrange the equation to solve for P out. We substitute our known values, and we end up with an output power of approximately 200 watts. Now let's look at a couple of examples of calculating the gain of a system in decibels using voltage. So we're given that Vin equals 500 millivolts, V out is 10 volts. What is the gain in decibels? So we start with equation 2, voltage gain in decibels equals 20 times the log of V out over V in. We substitute in our known values. The output voltage is 10 volts, the input voltage is 500 millivolts, and we get a calculated value of approximately 26 dB. So let's look at another example. We're given that the input voltage is 1 volt, the output voltage is 500 millivolts. What is the gain in decibels? Again, we start with equation 2. Voltage gain in decibels equals 20 times the log of V out over V in. We substitute in our known values. The output is 200 millivolts, the input is 1 volt, and we get a value of approximately negative 14 dB. Again, notice the first example is an amplifier. The output is greater than the input. The gain is a positive value in decibels. The second example is an attenuator. The output is smaller than the input, and the gain in decibels is a negative value. Now we can also calculate the input or output voltage values of a system when the gain is given in decibels. So I can rearrange equation 2 as shown, that V out over V in equals 10 raised to the dB divided by 20 power. So if we're given that the input voltage is 1 volt and the gain of the system is 23 dB, what is the output voltage? Again, we start with our given equation, V out over V in equals 10 raised to the dB divided by 20 power. We rearrange the equation to solve for V out. We substitute in our known values for V in and the gain in decibels, and we get an approximate output voltage of 14 volts. Now, the examples we've looked at up to this point show the decibel being used to provide a logarithmic relationship between input and output. And again, either input power, input voltage, output voltage. But the decibel is also used to express absolute power levels. The one that is most commonly encountered is the dBm. So the dBm expresses an absolute power level where the output power or the power is referenced to 1 milliwatt. And this is shown in the equation that dBm equals 10 times the log of P out over 1 milliwatt. So with this absolute power level, again, the power is not referenced to the input power, it's always referenced to 1 milliwatt. So if you've ever had the telephone repairman come to your house and check the signal strength at the box outside your house and told you the signal level was 80 dB, this is what he was talking about, 80 dBm. If you've ever had satellite TV and you run a check on your satellite dish and it shows you numeric values on your television for the signal of different satellites, that value is expressed in dBms also. So let's look at an example. What is the output power level of 1 watt in dBms? So again, we start with our given expression or equation that power in dBms equals 10 times the log of P over 1 milliwatt. We substitute in our known values. 1 watt is the output power, and we calculate a value of 30 dBm. Now we also use the dBm for discussing or quantifying, if you will, signal levels for audio. And for this application, the dBm is defined as 1 milliwatt across a 600 ohm load with a 1 kilohertz sine wave. So the only difference between this description and the previous description is this specifies the 1 milliwatt is dissipated across a 600 ohm load. Now we can also use the dBm to make calculations when we're given voltage values, excuse me, where the dBm equals 20 times the log of V out over 775 millivolts. And the 775 millivolts we see here is simply the voltage value that's required to dissipate 1 milliwatt across a 600 ohm load. Now also in audio recording in particular, you may come across this term called the VU, which stands for volume unit. The volume unit is defined as 1 milliwatt across the 600 ohm load with a 1 kilohertz complex wave. So the only difference between the dBm for audio and the volume unit is the fact that the dBm is a sine wave and the VU is for a complex wave. And if you recall the presentation on alternating current, a complex waveform is that we see when we have harmonics added to the fundamental frequencies, such as with voice and or musical instruments. So mathematically, a VU is the same as a dBm, 10 times the log of P over 1 milliwatt, which equals 20 times the log of V over 775 millivolts. The only difference is the wave shape. Now, if you're old enough to remember reel-to-reel or cassette tape recorders, or if you've ever been in a recording studio, you'll see the VU meter is an analog meter, and a portion of the scale is black and a portion of the scale is red. And of course you'll have some kind of pointer for the analog meter, and of course we always see up at the top of the meter VU. And on this VU meter, you'll note that this point is denoted as 0 VU or 0 dBm. And in recording, we want to try to adjust the amplitude or the volume of the audio signal coming in to where this needle doesn't go into the red area, because that's when we start overdriving the amplifiers and can run the risk of distorting the signal. Now, in electronics, things get a little bit confusing because the dB can be used or is used to describe other absolute levels. So we have to, I won't say pay attention, but be aware that the dB can describe things other than an absolute power level with respect to 1 milliwatt. Now, in the field of electrical power and power distribution, they use the dBW, which references a power level to 1 watt rather than 1 milliwatt. And for electrical power distribution, they also use the dBV, which references a voltage to 1 volt, and this is an RMS voltage. Now, the dB is also used to express levels of noise power. The dBRN is an electrical noise level that's referenced to 1 picowatt of power. And in, again, the world of recording or acoustical engineering, you may see the dB rap, which is a power level reference to 10 to the negative 16th watts. So this is a level of acoustical power. And you may also see the dB SPL. SPL stands for sound pressure level. So this is a logarithmic value of sound pressure that's referenced to 20 micropascals. 20 micropascals is the quietest sound that a human can detect. So in this presentation, we've looked at, of course, the logarithm to provide a foundation for understanding what that logarithmic expression for decibels is. We've looked at the logarithm to express a logarithmic ratio of power levels and a logarithmic ratio of voltage levels. We've also looked at the decibel used to express absolute levels of power and voltage. The most commonly used value is the dBm, which gives us a power level reference to 1 milliwatt and a voltage level of 1 milliwatt across 600 ohms, which is some voltage level reference to 775 millivolts.